Hi all, once again I welcome all of you. As I told you yesterday, today we will be talking about few important questions which we can expect for NEET exams. And I told you we will be discussing from chemical bonding. So let me start with my first question. Here we have a H2O2, HCN, cellulose and acetic acid. And out of these compounds, which one possesses intramolecular hydrogen bond? As you know, we have a two kind of hydrogen bond. So let me write there. So we have a two kind of hydrogen bond. First is called intermolecular and second is called intramolecular. So first one is called intermolecular. Second one is called intramolecular. See, first case, I am holding the hand of other person. But second one, intra, I am holding my hands together. So what are the examples for intermolecular? And what are the examples for intramolecular? See, the most common example that we need to be familiar with, intermolecular hydrogen bonding. You know, you have a HF. Next molecule, you know, you have a ammonia. And next molecule, water. So apart from this, H2O2, HCN, concentrated acetic acid or acetic acid. These molecules possess intermolecular hydrogen bonding. But if we talk about intramolecular hydrogen bonding, and we have one of the most common example, orthonitrophenol. See, I'm just drawing the structure of orthonitrophenol. See, we have oxygen atom and here H phenol. Next, we have a nitrogen, coordinate bond O, then double bond O. Here we have a hydrogen bond. You can see that it's just like holding the hands together. So here, intramolecular hydrogen. And you know this compound, this is what called as orthonitrophenol. So you know what is the name of this compound? This is what called orthonitrophenol. Similarly, we can say orthonitrobenzoic acid. See, let me draw the structure of orthonitrobenzoic acid. See, we have in this manner, and here we have a C, let's say double bond, and here we have a O, here we have a H. Then you have a N, coordinate bond O, here double bond O, here also you can see that you have a hydrogen bond. And you know, the first compound is called orthonitrophenol, but the second compound is called orthonitrobenzoic acid. So these are few examples for intermolecular hydrogen bond and intramolecular hydrogen bond. And now, what the advantage of intermolecular hydrogen bond? The compounds having intermolecular hydrogen bond will have a higher boiling point. Say for example, whenever you are comparing orthonitrophenol and paranitrophenol, in paranitrophenol, we don't have intramolecular hydrogen bond, but we have only intermolecular hydrogen bond. So as a result of intermolecular hydrogen bond, para will have a higher boiling point and ortho will have a less boiling point. See, at this time I want to talk about one more compound. You might be familiar with that. It's nothing else called copper sulfate 5H2O. So copper sulfate 5H2O. What the speciality of this particular compound? You know, in this compound we have a ionic interaction, we have coordinate bond, we have a covalent bond, we have a hydrogen bonding. So all type of bonds can be shown in case of a copper sulfate 5H2O. If I draw the structure of copper sulfate 5H2O, you can see that we have copper 2 plus and it is surrounded by 4 water molecules. See, I'm just drawing 4 water molecules. See how many water molecules are surrounded? 4 water molecules. And what's the bond? It's a coordinate bond. And copper is carrying a 2+ charge. And now the coordination sphere is closed. And outside you have a S of 4. So S double bond O, then you have a O minus. Here also what's there? O minus. So sulfate is there outside, isn't it? Now by connecting this sulfate and inside coordination sphere, we have one water molecule, it will be just like this. O, it not inside the coordination sphere, it will be outside. Here OH, here OH. Then here we have a hydrogen bond, here also hydrogen bond. Similarly, you can see that hydrogen bond exists with these atoms. So in that way, this compound is also important. Copper sulfate 5H2O, it's an example for a compound which shows all type of bonds. Ionic bond is there, coordinate bond is there, covalent bond is there, hydrogen bond is there. Now, so we are talking about hydrogen bonding. We know we have two kind of hydrogen bonding, intermolecular and intramolecular. And we have set some example. And I have told you H2O2, HCN and acetic acid, these are example for intermolecular hydrogen bond. And now only one is left with. That's a polymer. What is that polymer? Cellulose, isn't it? So in cellulose structure, we know we have a hydrogen bonding exists. So that's nothing else, intramolecular hydrogen bond. So our answer in this case is cellulose. All other things are example for intermolecular hydrogen bond. So in second question, what they are talking with? So we have 3 compounds, NO2 plus, NO3 minus, NH4 plus. What is the hybridization of central atom nitrogen in all these compounds? So let's see the compounds one by one. First one, we have a NO2 plus. Second compound, you have a NO3 minus. Similarly, we have a next case NH4 plus. See, to find out what is the hybridization, you need to find out the number of valence electron. So what I'm doing here, first of all, I'm just calculating sigma of valence electron. So first of all, I'm calculating sigma of valence electron. You know how many valence electrons are there in nitrogen? 5 valence electrons are there. And in oxygen, how many valence electrons are there? We have a 6 valence electron. So I can write there sigma of valence electron equals 5 plus 6 plus 6. But there is a positive charge. Positive charge means we have taken as that electron out. So we have to reduce, or we need to subtract 1. So what do you get? You get ultimately this will be equal 16. So we got the number 16. Here sigma of valence electron is 16. See, what we need to do next? Divide this number by 8. Maybe some in case you can see that it may not be divisible by 8, then we have some other strategy. But right now this number is divisible by 8. So I am just dividing by 8. So when we divide by 8, you get the number 2. And this number is the steric number which decides the hybridization. So what is the steric number? 2. So if the steric number is 2, the hybridization is definitely, that hybridization will be sp. So NO2 plus, what is the hybridization? It's given as sp. So let me go with the next question. Now let me go with the next compound, NO3 minus. Let's find out sigma of valence electron. Nitrogen, 5 valence electrons are there. And how many oxygen atoms are there? You have 3 oxygen atoms. So I can write there 3 into 6. And you have 1 negative charge. Negative charge means it's 1 more electron is extra there. So we need to add 1. Ultimately, when you add all these things together, you are getting the answer 24. So 24 is the number you got. Is it a multiple of 8 or not? Yes, it's a multiple of 8. Then what to do? So we need to divide here also by 8. When you divide by 8, you get the steric number 3. So if you get the steric number as 3, then obviously you can see that you will be getting the hybridization as sp2. So in first case, hybridization is sp. Second case, hybridization is sp2. So in NH4 plus, how about the hybridization? Let's see the number of valence electron. See, I'm just writing. In case of nitrogen, we have a number of electron is 5. And we have hydrogen. See, obviously you can consider hydrogen valence electrons 1. But in this method, don't consider the valence electron of hydrogen as 1. Instead, whenever you get hydrogen, consider it as 7, which is similar to halogen. So let me write 5 plus 4 into 7. Actually, even if you are using 4 into 1, then also you will get the answer. But the same method we can utilize to find out how many lone pairs and how many bond pairs are there. So there we cannot go with the number of electron as 1. So here itself we are practicing, whenever we are getting hydrogen, instead of hydrogen, we have to consider the electron of halogen atoms. That's all. So we get 4 into 7 minus 1. So what ultimately get? 4 into 7, 28. 28 plus 5, it will be 33. 33 minus 1, 32. So what the number you got right now, it's 32. Fortunately, here also you can see that you have got number which is a multiple of 8. So what to do here? Divide it by 8. So when you divide this by 8, you can see that you get the number 4. And this is a steric number here. See, when you got steric number 2, you got the hybridization sp. When you got the steric number 3, you got the hybridization sp2. When you got the steric number 4, obviously the hybridization will be sp3. sp3. So the right answer in the given options, is sp, sp2, sp3. So what's the answer here? sp, sp2, sp3. So in all these examples, in all these compounds, you might have seen that the sigma of valence electron comes as 8. But in case if it is not coming as 8, what to do? See, I am considering one example. It's a PCl3. So we have the compound PCl3 here. PCl3, let's find out the number of valence electron. Phosphorus has 5 electron. Chlorine has 7 electron. So we'll be getting 5 plus 3 into 7. See what you get? 21 plus 5, 26. So right now you got the number 26 and you know that it's not a multiple of 8. What to do this time? Nothing else. See, here we got a number which is not a multiple of 8. What to do? Split this number such that one is multiple of 8 and the remainder. See, I am doing that process. I am splitting this number such that the biggest number is the multiple of 8 and the remainder. So we will be getting 24 plus 2. 24 plus 2. Divide 24 by 8 and divide this by 2. What do you get there? You are getting 3 plus 1, which is equal to 4. So we got the steric number right now. What is the steric number? 4. If the steric number is 4, hybridization compulsory, you know that, sp3. So this is an extra example I added to your problem. Yeah, let's see to the next question. The correct geometry and hybridization of HCF4 molecule. See, I have told you right now how to get the hybridization. In the same manner, first of all, let's find out what is the hybridization. Then let's think about its geometry. See, Hc is a noble gas. The number of valence electron is 8. So I can say that sigma of valence electron equals 8 plus, how many fluorine atoms are there? 4 fluorine atoms are there. So we have 4 into 7. Total, 4 into 7, 28 plus 8. 28 plus 8 means 36. So I can write here it's equals 36. I have told you in earlier problem, if the number comes as a multiple of 8, then it's okay. But if it is not coming as a multiple of 8, then split that number into 2 such that the big number is a multiple of 8 and the other remainder. So what to do? 36 can be written as 32 plus what next to 4. See, 32 plus 4. So I am dividing 32 by 8 and 4 by 2. So what you get here, that's also important. See, 32 by 8, you get 4. And 4 by 2, you are getting 2. See, 32 by 8, you are getting 4. 4 by 2, you are getting 2. See, 4 plus 2, definitely, you will be getting 6. 6 is the steric number. Means hybridization is sp3d2. So I can say that from the steric number 6, hybridization is sp3d2. Whereas if you want to know about the geometry, we need to know how many lone pairs and how many bond pairs are there. See, the number 4 we got by dividing 8, that is the number of bond pair. So the number of bond pair is equal to 4, and the number of lone pair, the number that you get from the remainder, lone pair is equal to 2. So we have got number of bond pair 4, number of lone pair 2. Means here this is a kind of molecule AB4L2 type. This is what kind of molecule? AB4L2. AB4L2 means it will be square planar compound. So how about the geometry? Let me draw here. You can see that the geometry of the compound will be in this manner. See, we have a XC here at the center and a fluorine in a plane. But 2 lone pairs are there. 1 lone pair up and 1 lone pair out, and you have a geometry. So the right answer here, sp3d2, and what is the geometry of the compound? Square planar. So your answer is sp3d2 and square planar. So remember, see, if you are not getting the exact multiple of 8, what I have done, I have split it into 2, then I divided the first number by 8, second by 2. So anyway, our answer is sp3d2 and octahedral. Let's go with the next question. So in this question, they are given some species O2, O2 minus, O2 plus and O2 2 minus. What is the correct order of stability? See, if we want to know the stability order, definitely we want to find out the bond order. But for bond order, we need to find out the number of electron. So let me find out the total number of electron. So what is the total number of electron here? Obviously, you know that it is 16. So the number of electron involved in first case equals 16, and next case, you know that it's 17, next it's 15, next it is 18. So this is the number of electron present. Actually, see, here we have a methods to solve, like we need to write all the MO concept, but that's not required. See, we have to consider the basis nitrogen. Nitrogen bond order is 2, and oxygen bond order is 2, isn't it? So nitrogen bond order is 3 and oxygen bond order is 2. I'm just writing that. Nitrogen, what is the bond order? So nitrogen, your number of electron is equal to 14 and its bond order is equal to 3. So nitrogen number of electron is 14 and its bond order is 3. Now, please see to that whenever the number of electron increases, bond order decreases. Please keep in mind. How much it decreases? 0.5 decreases. So here, next species, we have a number of electron 15. What will happen to the bond order? Bond order becomes 2.5. Similarly, for next one, 16, what is the bond order? Bond order is 2. And for next 17, what happens with the bond order? 1.5. Next, we have a 18. What is the bond order? 1. 19, bond order is 0.5. 20, bond order is 0. So, in this, we have some species, 16 is there. So, what is the bond order of 60 electrons? When we have 16 electron, bond order is 2. So, let me write, this is what number of electron and bond order. So, if you write the bond order, here your bond order is 2. Next case, 17, bond order is 1.5. Next, 15, bond order is 2.5. Next, 18, bond order is 1. Whenever you have a higher bond order, its stability is higher. So, who is having the higher bond order? Definitely you know that O2 plus has the higher bond order. Let me take out that. This is having the highest bond order, highest stability. So, I am just writing O2 plus, next O2 and next O2 minus, next you have a O2 2 minus. This is the correct order of stability. Hence, the right answer in the option, it's 3. See, I have told you, don't practice, don't try to write the entire MO theory over here. Nobody will ask about that. We just want to produce an answer. For that, you consider nitrogen as a base. So, from that thing, you just think about and try to get the answer. So, let's see with the next question. Here, actually, they had given all these species and they're asking maximum bond angle in which case. So, in order to say about maximum bond angle, first of all, we need to see whether the geometry are same or different. Now, by seeing itself, we can see that geometries are not same. Okay, anyway, let's see to the hybridization. You know the rule to predict hybridization I have already discussed. So, again, going behind that is not good. So, in case of NO3, you can see that hybridization comes as sp2. So, the here hybridization sp2. Similarly, in NO2 also, you can see that hybridization is sp2. And in NO2 minus also, hybridization is sp2. While in the last case, you can see that the hybridization comes as sp. See, I have told you already how we find out the hybridization. Based on that rule, I have find out all the hybridizations. So here, these three are of sp2 hybridization. The first one is of sp hybridization. Our question is, which one has the highest or maximum bond angle? Definitely you can see that wherever we have a sp hybridization, there will have a highest bond angle. So no need to go after further. Directly you can select the answer. Which one has the highest bond angle? NO2 plus has the highest bond angle. But let's be familiar with their shape. These three molecules shape. So let's see to that NO2 plus. You can see that NO2 plus, so N double bond O, coordinate bond O. Here we have a positive charge. So this is the first compound what we have. NO2 plus. And you know this is a linear structure. And when you mind NO2, you know NO2 has a speciality. What the speciality? It's a molecule which contains odd electron. So that odd electron is present here. See to that. We have a N, then double bond O, here coordinate bond O, then we have lone pair, but only one electron. So the repulsion is not that much. And when you come to the next one, you can see that N, here lone pair electrons are 2 right now, then you have a double bond O, then we have a coordinate bond O. Here repulsion is more. If the repulsion is more, bond angle is less. So when you compare these three, where we have a maximum bond angle, first one has maximum bond angle, then next one, then next one. And here two lone electrons are there, hence repulsion is more, so bond angle is less. And the last case, obviously, can think in that way. So listen, we have seen the hybridization of each and every atom first of all. And then we compared the hybridization. We have seen that in all these cases, this is P2, but the last one is SP. So directly we can select the last one as the option. But remember, these three compound structure is important. So I have shown that first one is perfectly linear. There we have positive charge. But in this case, we have a lone electron. And this compound speciality, it contains one odd electron. But in NO2 minus, one more electron will come. So that odd electron concept is not there. So you have got the structure like this. So next question on board. See, we have CH2Cn twice, HCO3 minus, HCO4, Cn twice, where we have an equal number of sigma and pi electrons. And in order to answer for this, obviously we know we need to draw the structure of these compounds. See, I am drawing the structure one by one. First one, we have a CH2Cn twice. So we have C triple bond N. Here also C triple bond N. Next, hydrogen atom here. Here also hydrogen atom. How many sigma bonds are there? How many pi bonds are there? In this case, here we have 2 pi bonds. Here also 2 pi bonds. But how many sigma bonds? 1, 2, 3, 4, 5, 6. So we have 6 sigma bonds and 4 pi bonds. Here the number of sigma and pi are not equal. So definitely this is not our answer. And let's go with the next structure, bicarbonate. In bicarbonate, you can see that we have C double bond O, then OH, then we have a O minus. See, by looking at this compound, you can see that we have only 1 pi bond and the rest, almost 5 sigma bonds are coming there. So here, definitely by looking at this compound, you will say that this is not your answer. And let's see with the next compound. Next compound hybridization is sp3. And what the shape of this compound? See, I'm just drawing here Hc, here double bond O, here double bond O, again double bond O, double bond O. See, everywhere we have multiple bonds. And whenever we have multiple bond, one bond is sigma and the next one is pi. So here one multiple bond, 1 sigma, 1 pi. Another multiple bond, 1 sigma and 1 pi. So everywhere we have sigma and pi. So that in this case we have a 4 pi and you have a 4 sigma. This will be your answer. So you have one more option left with. Let's see what about that. That compound is the Cn twice. In Cn twice, you can see that we have a C triple bond N. Again, we have C triple bond N. How many sigma bonds are there? Only 3 sigma bonds. And how many pi bonds are there? 4 pi bonds. So this is 1 pi bond. This is another pi bond. Here also 1 pi. So we have a 4 pi bond and 3 sigma bond. So this is not our answer. This one also not our answer. This also not our answer. So only one is left there with answer is HCO4. In this particular question, they're asking which of the following compound has highest dipole moment. See, the dipole moment of a compound is decided by its structure. See to the structure of the compound. In carbon dioxide, you know that we have a C double bond O and here also double bond O. Here dipoles are in the opposite direction, so one dipole to this side and next to the opposite side in equal magnitude. So what will happen with the resultant? Resultant comes as a 0 here. So resultant is 0 in this case. And similarly, when we come to CH4, you know CH4 has a tetrahedral shape. So tetrahedral shape means we'll be having the molecule in this manner. C, here we have a H, next hydrogen to this side. Here we have a next hydrogen in this way. See, you know tetrahedral means one of the most symmetric structure. Here all the bonds are equidistant and they are maintaining equal angle. So all the bonds are CH bonds. So they will cancel each other and the net dipole moment in this case will be equals 0. And now only two options left with. What are those options? You are familiar. It's NH3 and NF3. So when you talk about NH3 and NF3, see to that, I'm just drawing the structure of both the compound. Both the compound has a same kind of structure. See, one lone pair here. Next we have a H. Here also H. Here also H. You know, you say for this structure as pyramidal. Now, next here NF3. So here also lone pair. Next F. Here F. Here F. Actually, this is a point which is very clearly given in NCERT. Out of these two compounds, which has the highest dipole moment? Our answer is, we know ammonia has the net dipole moment or highest dipole moment. Why ammonia has highest dipole moment? You see, what about the alignment of their dipoles? In NF3, you can see that the lone pair dipole is tending to be away from the center. And here, fluorine atoms are pulling downward. So, fluorine atoms are pulling downward. So, some part of the dipoles are cancelling each other. But in the second case, you can see that the lone pair dipole upward. And see to that nitrogen and hydrogen. Two atoms involved here. Who is having more electronegativity? Nitrogen. So, nitrogen will pull the electron towards itself. Means the net dipole moment in this case will be upward. So here the net dipole moment will be upward because both the dipoles are in the same direction. But in the next case, both the dipoles are not in the same direction. Hence the dipole moment will be less in this case compared with ammonia. Actually, this is a statement which is given in NCERT. This is one of the examples they have given in NCERT. So we have a lot of other examples for dipole moment. You might be familiar with that. See, suppose if I am drawing a compound here BF3, whether this compound has dipole moment or not. See, I am just drawing one molecule BF3. You tell me whether this compound has any dipole moment. No, this compound do not have dipole moment. Why this do not have dipole moment? Because fluorine atoms, 3 fluorine atoms equally spaced. So their net dipole will be cancelled each other, like in the case of CH4. So this compound has a dipole moment mu equal to 0. Similarly, we can write another molecule BCl2. What about the dipole moment in this case? Here also you can see that 2 dipoles are there in the opposite direction and they are getting cancelled. So here also dipole moment equals 0. And now when we consider another example, see to that, you know, we have 1,2 dichlorobenzene. Here chlorine, here also chlorine. You know, 1,2 dichlorobenzene. And next compound, I am just writing here. See, 1,3 dichlorobenzene. And what the next compound? Obviously, you know, 1,4 dichlorobenzene. See, out of these two compounds, which one has the net dipole moment highest? Here you can see that whenever you are seeing to the last case, both the Cl are in the opposite direction. So the net dipole moment is getting cancelled each other. So in this case, dipole moment is equal to 0. But in these two cases, dipole moment is not equal to 0. So here dipole moment is not equal to 0. And now among this, which one has highest dipole moment? If the angle decreases, dipole moment increases. So which one has the highest dipole moment? First one has the highest dipole moment, then second one, and the last for 1,4 dichlorobenzene. So in the next question, they are discussing which of the following has, or which of the following is a polar molecule. See, this is a continuation of earlier problem what we discussed. And you know what about BF3? BF3 is a symmetrical molecule, so it do not have any dipole moment. So let me cancel the option BF3. BF3 is not our answer because it is not a polar molecule even though it contains polar bonds. See why this is a non-polar molecule, because you know that you have a equally spaced BF bonds. So the net dipole moment is getting cancelled each other, and in this case you have a dipole moment equal to 0. Similarly, let's come to the next molecule. Next molecule is HCF4. So you know, earlier I have drawn the shape of HCF4. You know, it is a square planar shape. So I am just drawing here HC, and we have fluorine atoms. So here we have a fluorine, next fluorine in this manner, here also fluorine, here also fluorine. And not only this, we have two lone pairs in this manner. See, in this case, these two lone pairs are in opposite direction, so their net dipole moment is cancelling each other. And these two fluorine atoms in opposite direction, that will cancel each other. This also will in opposite direction, that also will cancel each other. So the net dipole moment in this case also equal to 0. So our answer is not HCF4. Now we are left with the two options, SF4 and SIF4. See to that. Let me talk about SF4. You know, you might have heard about the shape of SF4 molecule. Shape and hybridization of SF4 molecule. It has sp3d hybridization, and the shape of SF4 is seesaw shape. So let me draw the structure of SF4. It will be just like this. I can draw the structure. S at the center, F here, here also F. Next, you have a fluorine here, here also fluorine, and here one lone pair. See, in this case, these two dipoles will get cancel each other. But here, this is lone pair. And these two are definitely different molecule. So what will happen there? Their dipoles are in this direction, but lone pair dipole in this direction. So here, these two dipoles are not same, then it is not getting cancelled. So here dipole moment is not equal 0. Means this compound is a polar molecule. But when you think about, so this molecule is a polar molecule. But SiF4 is just like CH4, just like CF4. It is a tetrahedral shape. All the bonds are equal. So definitely what will happen? This is also not polar. But here I would like to say two more compounds. See, I am just writing one compound, PCl3F2. And the next compound, PF3Cl2. Out of these two compounds, which is polar and which is not polar? So let me draw the shape of a PCl3F2. See, whenever you are drawing the shape of these two molecules, you need to mind one thing. See, anyway, I am drawing the shape of these two molecules. Phosphorus at the center. And next, you have a fluorine here. Two fluorine atoms here, and Cl here, here also Cl, here also Cl. See, these three chlorine atoms, they are equal in magnitude. Their dipoles are getting cancelled. And here F on the axial bonds, that also will be cancelled. So then you may ask one question, sir, is it possible to keep fluorine in the axial itself? Yes, no doubt. See, in this structure, in trigonal bipyramidal structure, the most electronegative need to be kept in axial. So I have kept a fluorine in the axial. So this compound, fluorine cancel each other. 3 chlorine atom equally spaced cancel each other. This compound has no dipole moment, which is equal to 0. But whenever we come to the next molecule, there is some scenario. See to that, we have a phosphorus at the center. And here I need to keep fluorine. Here also I need to draw fluorine. Here also fluorine. Next chlorine. Here also chlorine. See, in this case, I am not keeping 2 chlorine atoms on the opposite side. Why? I told you the statement earlier. The most electronegative need to occupy the axial bonds. So fluorine occupy the axial bonds. These two will cancel each other, but these bonds do not cancel each other. So in this case, net dipole moment is not equal to 0. So please remember, the first one is non-polar, second one is polar. So let's see to the next question. Which of the following compound is paramagnetic? See, we have the species. First one, O2 minus. Next, Cn minus. Next is NO plus. And the last one is carbon monoxide. You tell me which one is paramagnetic here. See, if you want to know whether the compound is paramagnetic or not, first of all, we need to say the number of electron. So let me write the number of electron. Here the number of electron comes as 17. Here the number of electron comes as 14. Here the number of electron comes as 14. Here also number of electron comes as 14. You will select the answer O2 minus. Because in all other cases you have the same number of electron. And you know especially that is 14. 14 means bond order is 3 and that compound is diamagnetic that we studied already. So what about these compounds? These compounds are definitely diamagnetic because they do not contain any unpaired electron. But this compound, isn't it? It contains one unpaired electron and this compound is paramagnetic. See, normally what to do? You will write electronic configuration to find the magnetic moment. But that's not required. By seeing the number of electron, we can predict whether the molecule is magnetic or diamagnetic. See to that. See, I'm just writing number of electrons here. Here number of electrons 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. Up to 8 first of all let's discuss. You know what about their bond order? See, bond order will be coming like this. So I'll write bond order. Bond order will be 0.5, 1, 0.5, 0. Next again we'll get 0.5, 1, 0.5, 0. So this is the bond order. And what about the magnetic moment? See, magnetic moment will be, this is paramagnetic. This is diamagnetic. This is paramagnetic. This is diamagnetic. Next again, this is paramagnetic, diamagnetic, paramagnetic, diamagnetic. Up to 8, that is over. But after 8, see to that. We have a 9, 10, 11, 12, 13, 14, 15, 16. Let's see to that. Let's find out first of all bond order. What's the bond order in this case? 0.5. Next you get 1. Next you get 1.5. Next you get 2. Next 2.5. Next 3. Then you will get again 2.5. Next again 2. So here the magnetism can be written paramagnetic, again paramagnetic, paramagnetic, diamagnetic. So next paramagnetic, diamagnetic, paramagnetic, paramagnetic. This is a sequence what we require to solve the problem. See, writing the configuration and getting all those things, maybe it is easy, but better. See, if we have this sequence, if it is full, if we follow this, definitely we can come to the answer at the earliest. So you can use this table to find out whether the compound is paramagnetic or diamagnetic. So our answer is, which one is paramagnetic? 17 electrons means O2 minus is paramagnetic. So in next question, they're asking, which of the following has same bond order? See, if you want to find out bond order, we need to find out the number of electron first. So let's go with that. Number of electron here in NO. So nitrogen has 7 electron, oxygen has 8. So totally 15 here. Next, carbon monoxide 14. So compulsory, this is not our answer. Because if we need same bond order, we need same number of electron. So that's not obeyed here. And next, by seeing itself, you know, nitrogen means 14 electrons, oxygen means 16 electrons. So here also number of electron is not same. So bond order is not same. Similarly, O2 2 minus. What about O2 2 minus? In O2 2 minus, you have number of electron 18. So number of electron 18 comes there in O2 2 minus. And what about B2? B2 means, you know, lithium, beryllium, boron. Boron means 10. So I can write there number of electron present in one boron is 5. Since we have 2 boron, 10. Next, O2 plus. What about O2 plus? It's 15. Similarly, what about NO plus? You know, nitrogen 7, oxygen also 7 there because we have positive charge. So we'll have there 14. Anyway, these two are not our answer. This is not our answer. This one also not our answer. Because we know whenever 15 comes there, bond order is 2.5. And whenever 14 comes, bond order is 3. For nitrogen again, you know, bond order is 3. And for oxygen, here bond order is 2. And in the last case, 15 again comes as bond order is 2.5 and this is 3. So only one option is live there. What is that option? 18 and 10. So 18, what is the bond order? In this case, you can see that bond order is 1. And in case of 10, see, I have written earlier one table. You know, how about that table? You remember, I have written already once again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see, these are number of electron. Then what about the bond order? So 0.5, 1, 0.5, 1, 0.5, 0. Again 0.5, 1, 0.5, 0. Again 0.5, 1. So what is the bond order there? It's 1. So for these two, we have a same bond order. So these two are option C comes as your answer. Actually, this rule is applicable for most of the species except only one. But that is the most important. So you know what is the bond order of carbon monoxide? See, carbon monoxide means number of electron is equal to 14. If the number of electron equals 14, its bond order is equal to 3. Whereas, when you think about CO plus means right now number of electrons becomes 13. If the number of electron is 13, we are expecting a bond order is 2.5. But in real practice, you can see that bond order of carbon monoxide plus is not equals 2.5, but instead it's equals 3.5. See, this is one of the exception for MOTL. And why this is coming like that? Actually, it is believed that one of the electron is removed from bonding CO molecule, no, anti-bonding orbital. Since it is removed from anti-bonding orbital, bond order increased to 3.5. So this is one of the exception for or MO theory. In MO theory, you can see that normally what we expect for carbon CO plus, it's 13, but your answer, instead of 2.5, you will be getting 3.5. So these are the few questions which I have selected from this chemical bonding. And tomorrow let us discuss about periodic properties. Thank you for today.